But we still don't know anything beyond that. There are pieces. Okay, great, awesome, woohoo! Now, just so happens, remember we said that up to this point, science had really sort of been the province of rich white guys who were working with either like their family's loads of cash or somebody else's loads of cash, patrons and all that. We're starting here to see the beginnings of a different kind of system where a lot of scientific work is happening in really what are beginning to be research institutions and universities. We're starting to have this sort of academic bent. And in a lot of ways, science is a parlor trick. It's a really good parlor trick. So at this period, you have, like the Royal Academy of Sciences and organizations such as that perform sort of stunts, You have scientists who are delivering lectures to groups showing off all the neat things they can do. And one of them is this thing. So this is called a cathode ray tube. And when you were researching cathode ray tube, you probably came up with lots of pictures of old TVs, because that, in fact, is nothing but a modified cathode ray tube. So cathode ray tube is very simple. We could make one here. We have tried to make one here with, well, interesting results. If we gave you a piece of glass tubing and a couple pieces of copper wire, and you heated up the ends of that glass tubing until it was glowing hot and you could smush it. And you smushed it around the glass wire. So now you've got, imagine this, a glass tube with a piece of wire sticking out of each end and it's completely sealed on the ends. Can you visualize this? Now you're going to essentially punch a hole in the middle of the glass tube and stretch that out into a little sort of extra tube that you can put a suction hose on and you can suck all the air out of. So now what do you have? You got a tube with very little air in it. It's a low pressure environment. And sticking out of each end is a piece of metal. That's a cathode ray tube. You can make one. We tried it in here one year. I'll tell you about that in a little bit. So the neat thing is, and this had been well known for a long time, when I talk about science as a parlor trick. You take the cathode ray tube, you apply electricity to one end of one of the wires that's sticking out, and it glows. That's so cool. It's a great parlor trick. If it glows, it's even better. So you get this beam of light inside, and they called it a cathode ray. Okay, great. What do you do with that? Well, all kinds of things. What is it? One of the questions science always asks. What is it? Well, J.J. Thomson, Cavendish Lab, which I believe it's either Oxford or Cambridge. I can never remember. So, Thomson starts sort of playing around with the cathode ray tube. And a lot of people had. I mean, understand that lots of people were doing work with cathode rays. Thomson just happens to make some observations and correctly understand what they're telling him. So one of the first things that Thomson does is, remember, he had lots of graduate assistants, or minions, as we like to call them, who were doing his work for him in the lab. And they made little sort of paddle wheels, little sheets of metal, all joined up so they look like a little paddle wheel. And they could stick them on a track inside the cathode ray tube. Because remember, they're making their own cathode ray tubes. There's no science supply company where they go buy this stuff. They're making and improvising. And these guys are great experimentalists. A lot of the people who we're talking about here were building apparatus and equipment all the time. So he sticks this little paddle wheel in the path of the cathode ray, and it moves. It's on a little track, and it rolls down the little track. So let me ask you this. If you walked out in the hall, and there was a beach ball sitting in the middle of the hall, and it started to roll, so your observation would be that this ball is rolling down the hall. What could you infer from that? All of your inferences involve something hitting that ball. In order for it to move, doesn't a force have to act on it? Something physically has to hit it. Maybe it was, maybe Kira went out and kicked it because she just can't get enough kicking balls at soccer. So she went out and she whacked that beach ball and it's on its way. You know, maybe there was a gust of wind, maybe there was a fan, maybe somebody pushed it, but something hit it. Well, here's the other part of the parlor trick. So if you take this cathode ray, what do you know about charges? Let me back up. What do you know about charges? If I have two things that have the same charge, what do? They repel one another. If I have two things that have opposite charges, what do? They're attracted. So if you take a cathode ray tube and you put an object that has a negative charge up against it, the cathode ray bends away. It's an interesting observation, and it adds to the fun of the party trick. Woohoo! Look, look, look! If you put a positively charged object up against the glass, the cathode ray bends toward it. So you could spend hours just making the cathode ray go, which, you know, I'm sure somebody did when nobody was looking. So what's your observation? The ray bends away from a negatively charged object and towards a positively charged object. Yeah, that would start to make you think, I bet this thing is negatively charged. So we still don't know what this thing is. We still have no clue what the cathode ray is. Whoops. So what Thomson says is, you know what? They're little pieces. That's what they are. They are little chunks of something. They are pieces of something. And he says they've got a negative charge. Now, why did he say they were pieces? Why did he say they were actually physical particles? Because they had enough mass to move that paddle wheel. So just like our beach ball out in the hall, something with some amount of mass, whether it was wind, whether it was Kiara's foot, kicked that beach ball, hit it, physically struck it, and got it to move. So he's saying that if that ray can actually move the paddle wheel, it must be made up of little tiny pieces that actually have mass. It's a pretty good leap. You know, so your observation is just that the paddle wheel moves. What we can infer from that is, hey, this is made of actual physical pieces of matter. Now, what he proposes ends up being called the plum pudding model. This is not pudding like you and I know it. This is not a creamy and delicious dessert treat made from milk and eggs and cornstarch. A pudding in the British sense is usually like potatoes, flour, carrots, raisins, some spices, lard, and eggs, all made into this like heavy, thick dough and then put in a mold and steamed for hours. And it's really disappointing if you think pudding is what we think pudding is, but that's what they call pudding. So a plum pudding is this sort of circular, spherical, molded, steamed pudding. Nothing like what we think of as pudding. That's a sort of a raisin cake. It's not really a plum pudding, but when he said plum pudding model, that's what he was thinking. For a modern American mind, blueberry muffin model works better because you can all visualize a blueberry muffin. It's an object that's got blueberries randomly scattered throughout it. So that's what Thomson says an atom is like. He says, well, yes, it's this little thing, but inside that little thing are negative pieces. So, this is not 100 years after Dalton. Dalton proposes his atomic theory in 1808. This is not even the 20th century. Less than 100 years, and we've already broken Dalton's outline. What part of Dalton did we break here? So less than 100 years later, Thomson's saying, hey, Dalton, look, everything else is great, but you know what? There are smaller pieces. We can divide this. There is something smaller than the atom. There are subatomic particles. So we also know that atoms are electrically neutral. If something's electrically neutral and we know that there are negative pieces in it, what also must be true? Must be positive pieces. So the plum pudding model emerges, and it looks, you have this, spherical object, and inside it you have little negative dots and little positive dots. All nice and evenly distributed. Not that your blueberries ever end up perfectly evenly distributed. You always end up with some on the bottom and, whatever. But nicely distributed. Okay, well this is good. Now, because electricity was a relatively newer thing, there was a lot of excitement about electricity at this point, and so a lot of researchers were working with electrons and electricity. You understand, I think, that all electricity is a little row of electrons running at high speed through a medium. Later I'll ask you to visualize this as a bunch of divers lining up to jump off the high dive. It's just a row of electrons, and they're just flowing. They're just moving. So there was all this interest in electrons because they were a relatively new thing. So a few years after Thomson posits the existence of this negative particle, this electron, Millikan actually isolates them is the wrong word. He manages to figure out their mass and their charge. And the way he does this, it's kind of confusing when you read about it. So he takes a chamber, very much like what you see there, that's connected to a battery. And so he's able to put a charge on different parts of this metal chamber. He sprays very, very fine oil droplets into the chamber, and they have to pass down through a little tiny hole in the charged plate. So in doing that, the droplets themselves pick up a charge. So now we have these charged particles, and then he varies the charge in the plate above them and below them, and the amount of charge that he applies to those, to get them to suspend in midair. And so based on that suspension, he can, there's all kinds of math that's, way above my pay grade. He can figure out the force that's necessary to hold that particle, and from force you can back figure to mass, and from the amount of charge that it takes to balance the charge on the oil droplet, he can figure out the magnitude of the charge. It's physics. So from that, he figures out that electrons are really stinking tiny. Like tiny, tiny, tiny. Like incredibly, insanely small. They don't have a whole lot of mass. I know, and he figures out the charge. Now, if we've said that the inference is already made that if the atom is neutral and we have a negative charge, we have to have a positive charge. Since Millikan figured out how big the charge on the electron was, what else did he figure out? Without even trying. Okay. Well, so now at this point, what do we know about atoms? They can be divided. We know we've got these negative particles. And the best science that we know is this plum pudding model. That they're these little spheres of evenly distributed positive and negative charge. So now along comes, well, okay, first of all, let's, other things that flow out of this. So now we know about the electrons. We can infer that there's got to be something positive to balance them. It's got to have the same amount of charge. The other thing is we know that electrons are really, really tiny, so something else has to make them have mass. Because, they're what make up your mass. Your mass is comprised of lots of little atoms with their little mass. It's crazy when you think about it that way. Okay, great. We still don't know anything about what those positive pieces are. We still don't know anything about their mass and what contributes completely to their mass. So now we get to Ernest Rutherford. So J.J. Thomson's working at Cavendish Lab. Rutherford comes to work for J.J. Thomson. He's actually one of his students, one of his minions who's building equipment. And Rutherford is great because Rutherford is known as this, they call him the consummate innovator, experimenter, and basically we'd call him a MacGyver kind of guy. He's a farm boy. He's a farm kid from New Zealand. And New Zealand at this point is kind of like the Wild West. It's several thousand miles from England, yet these people are basically English culturally. And they're living in this sort of outpost of civilization, this far-flung remote frontier. These are frontier people, really. And Rutherford's one of a big family. And there's the quote that I can't find it again, but I've seen it a few times. And I haven't been able to scrape it back up. I think it must have been a biography I read. Later in life, he quoted his mother as saying, "Well, Ernest, we haven't the money, so you must be more clever." And, it really gets to, and if any of you are farm kids or no farm kids, that idea that, like, well, we may not have exactly the tool we need, but we're going to figure it out and we're going to make it work somehow. And, it might be duct tape and baler twine and, but we'll make it work. We'll figure it out. We'll improvise it. Well, that's kind of the spirit that Rutherford comes into the lab with. This, like, well, that's not working. Okay, well, let's just, let's jimmy rig it. Let's, well, what if we use this? Well, what if we, So he's a real, he's a great innovator because of that. Because he's got this sort of like, well, we'll wing it kind of attitude. And he's a great experimentalist. So they're working on, the whole we don't prove anything in science, we just disprove it. So they're picking away at this plum pudding model. They're trying to figure out more about the structure of the atom, the internal structure of the atom. And remember, and Rutherford, along with everybody else, everyone else at the time, believes and understands that the atom is this nice little even distribution of positive and negative charges. Whoops. Yay! Very neat, very nice. So knowing what you know about like and dislike charges, you can predict what would happen if the atom looks like this inside if you fire a positive charge at it. So Rutherford's big work was actually with nuclear radiation. The concept of alpha and beta emitters, these are different kinds of particles that something that's what we call radioactive can emit. And alpha emissions are positively charged particles. So if this is a lump of a radioactive substance that's an alpha emitter sitting there, it's throwing off these positively charged particles, these alpha particles. And alpha emitters, how you block radiation from an alpha emitter? Like that. The particles are so big they don't pass through most materials. So you can contain an alpha emitting radioactive material in a paper box and no radiation will come out. The particles are really big, but they're positively charged. So what Rutherford says, and they had been working with a variety of materials, a variety of metals, and they had been firing alpha particles at metals and figuring that there was a lot of empty space in between these positive and negative charges, so they should be able to get these alpha particles right through a metal. And they kept working with smaller and smaller thicknesses of metals until they got down to gold foil. So this was not the first thing that they fired alpha particles at. This was the last in a series of things that they fired alpha particles at. And this gold foil we're talking about, you can all visualize a sheet of aluminum foil. This was foil made of gold, pure gold, but pounded so thin that it's almost one atom thick. I mean, this is painstakingly difficult to work with because it's so prone to tears and it's very, very, very thin. So they're taking this gold foil and they're firing alpha particles at it. So if we take our little positive particle here and we fire it at this, well, it should more or less go straight through. Because, here where it's attracted by one and repelled by the other, it might jog a little bit one way and then it might jog a little bit the other way. So, there might be some wiggle in its path, but overall it should pretty much come straight through. There shouldn't be a whole lot of what we would call deflection. So deflection is when something bounces off something else and goes in a different direction. Dodgeball is an example of deflection. You're constantly using the ball to deflect someone else's ball. So, in this case, these more or less, they might bend a little bit here and there, but more or less they should go pretty straight through if the inside of the atom looks like what we think it does. Seems reasonable. So, Rutherford fires his alpha particles into the unknown. Into a black box. He has no idea what's there. How easy is it to figure out something that you can't see and you can't directly observe from just evidence? It's pretty tough. So he fires the alpha particles at them, and some of them do pretty much go almost straight through. And some of them are deflected a little bit. And then I think they said every 800th or so, like 1 in 800, do this. Right back at you. It's a ricochet, basically. So Rutherford is quoted at the time as saying, "It was as if we had fired an artillery shell at a piece of tissue paper and had it bounce back." And the metaphor that I like, that I think probably makes more sense to you, if you fired a rifle at a snow pile, just a big old pile of loose powdery snow, you would expect that they would all pretty much go straight through, right? What if every 100th bullet came bouncing right back at you? Ah! What would you begin to suspect? There's something in there. I don't know what it is, but snow doesn't act like that. Yeah, exactly. And so they keep firing alpha particles at this foil. And sure enough, every 800 or so, I mean, not with any regularity, obviously, but every now and then one comes pew, straight back at you. Woo! Now, of course, no, the alpha particles aren't really going to part your hair when they come back at you. These are pretty tiny. You can get hit with an alpha particle and you won't know it. But metaphorically, whoa, that is not what they expected. And remember that the best science happens when somebody goes, oh, that's weird. That's when we're actually figuring something out. So, based on that, Rutherford says, you know what? I think Thomson was wrong. I don't think those positive charges are all evenly scattered throughout the nucleus. I think they're all confined to one location. I think there's this, and it's dense, it's tight, it's this little tiny center. And I think that's where all the positive charges are. And he calls it the nucleus. So now we have this idea of a nuclear atom. My nucleus is not centered. You just have to imagine that that's a three-dimensional spherical object and you're looking at it from a three-quarter perspective. I'll blame art. So we suddenly have this new idea that there's this densely packed little thing. So if we imagine our snow pile that you're firing a rifle into, now we know that there's a steel baseball in the middle of it. And as long as your bullet goes past the steel baseball, you're fine. It's going out the other side. But man, if you hit that steel baseball, it's coming right back at you, and you better duck. You know. So we've got this tiny little dense center. This is the nucleus. And this is really good stuff. So Rutherford's model of the atom is the one that you see illustrated every place. This is the one that ends up on coffee mugs and T-shirts and science club shirts one year. And it's this guy. And it shows this densely packed nucleus, all these protons in the center, and the little electrons orbiting it. And it's often called the planetary model because it's a lot like the sun and a bunch of little planets. And they're just spinning in these little orbits around the nucleus. Now here's the problem. You know, with each of these steps, you go, well, yeah, that explains this really well, but what about that? There's a problem. Because if there wasn't a problem, people would have stopped thinking about this and would have just shut up and gone and done something else. But that's not the way it happened. So the problem here is, if you have a positive charged thing and a negatively charged thing, and you put them together, what happens? They stick together. So why don't these little negatively charged electrons get sucked into the nucleus? Rutherford says, I don't know. Somebody else will figure that out. No, he doesn't say that. But he doesn't have an explanation for it. How can those electrons be so close to that little dense bundle of positive charge and not get sucked right into its face like a little tiny spaceship orbiting the sun too closely? How does this work? So Rutherford's problem doesn't get answered for a few more years. But at this point, we now have two pieces. We know that electrons are outside the nucleus. We have the nucleus. So we have two parts of the atom, and we also have their locations. This is good. We're making a lot of progress here. And this is in what? Like Rutherford's early... So this is just over 100 years. That's pretty rapid fire, actually. So now we have the Joliot-Curies. Do any of you recognize either of those last names? Curie, anyone? Curie? Madame and Pierre Curie? No? Okay. So Marie Curie, really one of the first female scientists who gets any credit. Irene Curie was their daughter. And I believe Marie Curie won a Nobel. So Irene Curie is their daughter. She marries Frédéric Joliot. Anybody notice anything about that name? Joliot Curie? It's hyphenated. It's a hyphenated last name, which they both used. When she married Frédéric Joliot, they were both scientists, they were both researchers, and they decided to together adopt a hyphenated last name, which they both used and they published under, which was amazingly, awesomely progressive in 1932. Holy cow. You know, and it probably doesn't hurt when you have two parents who are famous scientists and you really don't want to give up your own last name. So yeah, the Joliot Curies were rather unlucky, as it turns out. I think it was 3 Nobel Prizes that they lost. Yeah, so the problem with science, you not only have to know what you're looking at, you have to know why what you're seeing is what's happening. So in this case, they were working with radioactive materials, with nuclear decay, and they were working on the problem of the atomic nucleus. There were a couple problems with the atomic nucleus. And I believe it was paraffin. They were firing high energy beams at paraffin, and they were getting it to kick off something. Paraffin, wax, in essence. They were getting it to kick off something, and they thought it was another form of energy. They believed that what they were seeing was like another form of energetic radiation. It wasn't. So Chadwick sees their results, because remember, in science, we publish our results, we discuss them so that other people can try to replicate them, and if nobody else can get what you got, then you probably did something wrong. Chadwick looks at their results and says, that's not what they have. I know what they have. He replicates the results. What they had was neutrons being ejected. They had neutrons being ejected from the material, but they didn't catch that. So Chadwick comes along, correctly explains what's happening, and he wins a Nobel Prize for it, and he gets the credit for the discovery of the neutron. 3 times that happened to them. There were 3 separate pieces of research where they had the results. They were observing a phenomenon, but they failed to interpret it correctly, or failed to interpret it in a timely enough fashion. Like, they probably would have gotten there, but they were a little bit slower on the uptake, and somebody else saw their stuff and went, aha! Poor Joliot Curies, and man, Chadwick was a lucky guy. So at this point now, and this is the early 30s, we know that there's a densely packed positive nucleus. We know that we have neutrons now in the nucleus? Woohoo! In the nucleus. And we know that we've got electrons outside the nucleus. Guess what? We've got the basis of atomic structure. Now's where it starts to get weird. This is actually where I will break this into part 2 and part 3, so I'm going to stop the recording. We'll take a short, well, we'll talk about some other things before the break, and then you'll do your 4 minutes and come back and we'll finish up with the weird stuff.